Hello everyone, my name is Vasilis Sarafidis. I'm a professor of finance at Brunel University London, and today I'm going to introduce a novel approach for estimating panel data models with unobserved common factors using Stata and based on the method of instrumental variables. During the first part of this video, I will introduce the basic ingredients of the methodology developed by my co-authors Guo Kui, Milda Norkute, Takashi Yamagata, and myself. In the second part, I will show you how to implement this approach in Stata, and for this purpose, I will introduce the package xtivdfreg, which has been recently written by Sebastian Kripkans and myself. The model we're going to focus is of this form here, where YIT denotes the observation on the dependent variable for individual unit I at time t. I is a cross-sectional index that goes from 1 up to capital N, and t is the time series index that goes from 1 up to capital T. Therefore, we observe a cross-section of n individual units, each one being followed over capital T time periods. On the right-hand side of the model, we have first of all an autoregressive component, that is the lagged value of y itself, which captures an essential feature in that economic behavior often depends on past own behavior. This phenomenon is known as state dependence or path dependence, and it is commonly attributed to things like costs of adjustment, uncertainty, technological constraints, habit formation, and so on. The vector x contains k individual specific time-varying observed characteristics known as covariates. Model covariates are typically used to establish causal effects. Finally, the unobserved error term, UIT, is composite. So epsilon reflects the usual idiosyncratic disturbance, while the other term here is the so-called common factor component. So F denotes a vector of m factors, whereas lambda is a vector of corresponding factor loadings. So the factor component absorbs different sources of unobserved heterogeneity. For example, F may absorb unobserved common influences or otherwise economy-wide shocks that hit the population of all individual units, albeit with different intensities. And these individual specific intensities are reflected by the factor loadings. Equivalently, the factor loadings may absorb different sources of unobserved heterogeneity across individuals, the impact of which varies over time in an intertemporally arbitrary way. As a simple example, suppose that we're interested in analyzing credit risk behavior among financial institutions. Therefore, YT represents a measure of risk for bank I at time t, while the lag-dependent variable captures bank-specific risk vulnerabilities that build up over time. In this case, X contains observed risk determinants such as bank size, asset liquidity, profitability, and so on. Thus, for instance, the coefficient beta corresponding to bank size reflects the extent to which larger banks take on average more risk than smaller ones. This is, by the way, the so-called too big to fail hypothesis. Finally, in this context, the factors may capture, for instance, different sources of market risk and economic conditions, such as interest rate volatility, house market fluctuations, business cycle fluctuations, private sector debt accumulation, and so on. The impact of all those factors is allowed to be specific to each individual bank, depending, e.g., on the quality of corporate governance of Bank I, the extent of exposure of Bank I to other financial institutions, and so on. Note here that the factor model encompasses the popular two-way error components model, which arises by setting m, the number of factors, equal to 2, and then imposing two unity restrictions on f and lambda respectively. Of course, the two-way error components model is highly restrictive most of the times because it imposes, for example, that conditional on a bank-specific fixed effect, all sources of market risk and economic conditions that we mentioned above have exactly the same impact on all individual banks, a restriction that is likely to be violated in practice. Before we depart, note also that further lags of y can also be accommodated in a straightforward way, and of course the model could also be static as well, without any lags of y or any lags of x. But what are the main difficulties associated with identifying and estimating the parameters of this model? Well, to begin with, we have there exist potentially three sources of endogeneity here. So first of all, the lag-dependent variable is endogenous by construction. That is, unless one is willing to impose highly restrictive assumptions, the lag-dependent variable is correlated with a common factor component. And that is for the same reason why in the two-way error components model, the lag-dependent variable is correlated with the individual fixed effect. Secondly, the model covariates may also be endogenous. For instance, the unobserved factors may influence not only the dependent variable y, but also the covariates. For instance, the quality of corporate governance may not affect bank risk only, it may also affect bank profitability and asset liquidity. At the same time, covariates can also be correlated with a purely idiosyncratic error as well, which is due to reverse causality, for example. Another issue that arises in this model is the so-called incidental parameters problem. If we wish to fully control for the common factor component, we'd like to treat f and lambda as fixed parameters. However, lambda varies across I and f varies across t. So as the sample size increases, the number of estimable parameters increases as well. In the best case scenario, this typically leads to asymptotic bias for estimators. In the worst case, it leads to inconsistency. Thirdly, in practice, we rarely know, of course, how many factors exist, which means that we need to estimate the number of factors from the data. And finally, it is possible that the strength of the impact of the observed characteristics x on y is specific to each individual unit. That is, the model is heterogeneous. In recent contributions, my co-authors and I developed a novel estimation approach for this model that we just described, based on the method of instrumental variables. Our approach is designed for large panels, meaning that n and t are of comparable magnitude. That is, neither dimension is negligible in comparison to the other one. For this type of model, two methods have dominated the literature, which have been put forward in the seminal papers by Pesaran 2006 and Bai 2009, giving rise to the so-called common correlated effects or CCE estimator and the interactive fixed effects estimator respectively. Several excellent papers have followed since, extending these two methods into several other setups. Unfortunately, we do not have the time to discuss such extensions, and it is beyond the scope of this video anyhow. Now, CCE and IFE complement one another. Our approach essentially fills in various gaps between these estimators and has several advantages over them. In particular, to begin with, our approach is free from incidental parameters bias, which means that it does not require any bias correction to achieve asymptotically valid inferences. Secondly, our approach does not require the so-called run condition, which is necessary for consistency of CCE. Thirdly, our method is linear and computationally very fast. In contrast, IFE relies on nonlinear optimization, and therefore convergence to the global optimum might not be guaranteed. Fourthly, our approach allows for slope parameter heterogeneity using a mean group type procedure. And finally, our approach allows for genuine endogeneity, such as reverse causality, so long as external instruments are available. In our Stata journal paper, where the Stata package xtivdfreg is documented, Sebastian Kripkans and myself provide further details. To begin with, I will provide a brief outline of our two-stage IV procedure designed for pool models, that is, models with homogeneous slope coefficients, and I will introduce the mean group estimator for heterogeneous panels a little bit later on. So in step 1, we project out the unobserved common factors that influence X using principal components analysis, PCA, and then we estimate the slope parameters of the model using instrumental variables with instruments constructed from defactored regressors. The resulting IV estimator, the first stage IV estimator, is consistent. In the second stage, we project out the factors that directly hit Y using PCA based on the first stage IV residuals, and subsequently we run another IV regression using the same instruments as in stage 1. To appreciate this in more detail, we're going to stack the observations of our model over the time dimension for each individual. This yields equation 2, where Y is a vector of order T, X is a matrix of dimension T by K, and F is T by M. In order to ensure that the X's are endogenous with respect to the unobserved factors, we are going to specify the following data generating process. Fx denotes the factors that influence X and is of dimension T by Mx, where Mx denotes the number of factors in X. Note a very important point here, which is that F and Fx may overlap, they may be identical, or they could be completely different but correlated. F and Fx could also be independent, but this case is trivial, of course, since the two-way fixed effects estimator would be consistent. Similarly, the factor loadings in X and the factor loadings in Y could overlap, they could be identical or completely different and correlated. Now, more compactly, we may introduce a new matrix C which contains both lagged value of y and x. This is of dimension d by k plus 1 with corresponding parameter theta, a vector of order k plus 1. Now let fx hat, comma minus L denote the principal component's estimator obtained based on the L's lagged value of x, where L goes from 0 up to zeta. The projection matrix that asymptotically eliminates the factors from x takes the usual form. So mfx hat is the usual symmetric and idempotent projection matrix. Thus, the matrix of instruments can be formulated in this way here. So this is the contemporaneous value of the defactored x, and the remaining matrices are the lagged values of x defactored. We adopt the convention here that x minus 0 equals x itself. So the zeroth lag of x is x. Now, this matrix has zeta plus 1 times k columns, and therefore the degree of over-identification here equals k times zeta minus 1. Our first stage IV estimator is of standard form as in equation 5, where matrices A, B, and G hat are defined accordingly. Now the first stage IV estimator is consistent, but it is asymptotically biased. So instead of trying to correct the asymptotic bias of the estimator, we proceed on to a second stage. And in the second stage, what we do is we project F using PCA based on the first stage IV residuals, which are consistent estimates of the true errors, and then project out F from the entire model and run another IV regression using the same instruments as in stage 1. Specifically, let f hat denote the PC estimator obtained based on the first stage IV residuals. The optimal two-stage IV estimator takes the usual sandwich formula expression where A omega and G double hat are defined here. The two-stage IV estimator is not only square root NT consistent, it is also asymptotically normally distributed, and it is also asymptotically unbiased. That is, the square root NT times theta hat has mean 0. Therefore, the estimator has correct size in large samples without requiring any bias correction. Now this is pretty much what the two-stage IV procedure involves for homogeneous panels. Before I move on to estimating heterogeneous panels, I'd like to talk about a case of major importance and high relevance in several empirical applications, which occurs when some covariates are endogenous, not with respect to the factor component only, but also with respect to the purely idiosyncratic error epsilon. This situation could arise, for example, under reverse causality, that is when x influences y, but at the same time y influences x. Now, our approach remains valid in this case, so long as there are external instruments available. This is a standard IV requirement. To illustrate, let we decompose X into a set of exogenous and a set of endogenous covariates. Note again here that exogeneity refers to contemporaneous correlation between X and epsilon, or lack of correlation, since the X's can always be correlated with the factor component. Now suppose that there exists a set of external variables which are exogenous with respect to epsilon. These could possibly be correlated with the factors. Now let x plus denote the matrix that combines the exogenous covariates and the external variables. This is of dimension t by k star. The two-stage IV estimator is actually identical to that in equation 6, except that the factors are projected from x plus as opposed to x itself, and therefore z, the instrument's matrix, is adjusted accordingly. Consider now the same model with heterogeneous slope coefficients. So for this setup, we put forward a mean group type procedure. In the first stage, and there is only one stage in fact, we project out the unobserved common factors that influence y using principal components analysis again. This step is identical to what we do for the pool model. Subsequently, we eliminate the overlapping factors between f and fx by projecting out fx from the entire model. The individual specific IV estimator of theta is given by this expression here. Note that unlike the pooled estimator, here we essentially conduct double defactoring in a single stage. That is, we use fx or mfx hat to defactor not only the instruments but also the entire model. This is in order to eliminate factors in y that overlap with those in x. One could also proceed to a second stage and obtain the PC estimator of f itself. However, since the individual specific first stage IV estimator is only square root t consistent, f can be estimated rather inefficiently. Finally, we obtain the MGIV, mean group IV estimator, by averaging individual specific estimates of the slopes. MGIV is square root n consistent and asymptotically normally distributed with mean 0. Therefore, it is asymptotically unbiased and has correct size in large samples without any bias correction.